Hello and welcome to this video about determinant proofs. In this video we'll prove this theorem, that the n-dimensional volume of a parallelepiped that is equal to the linear transformation of another parallelepiped is equal to the volume of this parallelepiped multiplied by the determinant of the matrix corresponding to this linear transformation. So I've written all the names of the different objects that we'll be using in this proof, and I've given these objects different colours depending on what they are. Like a region in n-dimensional space is coloured in orange, and a matrix is bright pink, and a linear transformation is purple. The identity matrix and unit n-dimensional volume region are coloured in blue. So now to make a sketch of this proof. Firstly, we'll define the n-dimensional cube U, which has an n-dimensional volume of 1. And we'll define this linear transformation T, which creates the solid P from the unit cube U, and this is its equation. And then we'll apply another linear transformation L to both sides to give us this equation. And then the matrix AB is the matrix corresponding to this double linear transformation LT, because a function concatenation of linear transformations gives us a multiplication of their corresponding matrices. So this matrix AB corresponds to the volume of the solid LP, and the volume of the solid P is given by matrix B corresponding to function T. So we can get the volume increase by dividing the volume of solid LP by the volume of solid P, which is just dividing these matrices. It's a sketch of a proof, so I'm allowed to put a division sign in to make it more clear to the person watching this video. So now to prove this theorem more rigorously, I'll write the statement of the proof and draw in the diagrams and try to prove it again. I've also decided to define this linear transformation L and its corresponding matrix A to be a matrix of row vectors v1 to vn, so that it can use a previous theorem 4-9. So now to start this proof, we can make this statement that the volume of this solid is equal to the absolute value of the determinant of the matrix that defines it, that contains all of the vectors that define it. We can call on a past theorem to state this. And this region called U is the n-dimensional cube that has all its sides equal to 1 unit. So we'll just draw it. It's a square in 2-dimensional space, and the linear transformation T maps it to the solid P. And the volume of this solid is 1, because all of its sides are 1 and at right angles to each other, and its corresponding matrix is the identity matrix that has a determinant of 1. So I'll just scroll everything up the screen here to make some more room. We can write this statement that the linear transformation T applied to the unit cube U is equal to the solid P. We can see this from the diagram. And so we'll set C to be equal to the matrix corresponding to the linear transformation T. We can apply the linear transformation L to both sides so as to get this equation. This can be rewritten as the product of all these matrices that correspond to these linear transformations and regions. For example, I corresponds to U. And then we can eliminate the identity matrix to get this product. Then we can multiply both sides by the inverse of A to get this equation. We can assume that A is invertible, otherwise it would give us a region with no volume. And these inverse pairs of matrices eliminate each other to give us this equation that tells us that B and C are the same matrix. So we can assume that B is the matrix corresponding to T from now on. So I'll make some more room on the screen to write more stuff. We can describe these regions using these functions in terms of the unit cube region U. We can multiply this equation by 1 to get this. We're allowed to unsimplify equations in proofs if there's a good reason to do so. Then we can substitute the volume of the unit cube in for 1 like this. We can make this substitution so that now everything is in terms of the unit cube region U. Then we can write out this equation. The matrix product AB corresponds to the combination of these two linear transformations L and T. We can split this determinant up into the product of these determinants using a past theorem. Then we'll split up this absolute value function into the product of these two absolute value functions. And then we can make this substitution like this so as to simplify this equation. Then we can make this substitution of L applied to the solid P so as to finish this proof, since this is the equation that we wanted. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.